In this lecture, you will learn about catalytic reaction kinetics. After this lecture, you will be able to describe catalytic surface reaction steps, derive and understand kinetic expressions using the concept of rate-limiting step and equilibrium, understand Langmuir, Hinshelwood and Eley Rideal mechanisms and kinetic expressions, and propose a mechanism and synthesize a rate law consistent with experimental data. As you have learned from your homogeneous reaction engineering, you need a rate law or a rate expression in order to design your reactor. Previously, we have talked about the 7 steps involved in catalytic processes for a two-phase packed bed reactor. I would like you to recall those 7 steps and do the little exercise that I have here. Can you match the boxes to the corresponding steps? I will give you 2 minutes. You can pause the video now. Did you get all of them? Step 1 is the transport of reactant A from the bulk to the catalyst external surface, which is an external diffusion step. Step 2 is the transport of reactant A through the pores to the internal surface, which is an internal diffusion step. Step 3 is the adsorption of reactant A onto internal pore surface. Step 4 is the chemical reaction whereby the reactant A is converted to the product B. Step 5 is the desorption of product B. Step 6 is the transport of product B from internal pore to the external catalyst surface, which is an internal diffusion step. Step 7 is the transport of product B from external surface to the bulk, which is an external diffusion step. Steps 1 and 7 are external diffusion steps, while steps 2 and 6 are internal diffusion steps. In this lecture, we will consider the catalytic reaction process, which comprises 3 steps: the adsorption of reactant A, surface reaction where reactant A is transformed into product B, and desorption of product B. In the succeeding lectures, we will consider internal diffusion and then external diffusion, and eventually, we will design the whole reactor based on the knowledge that we have of what takes place within and in the vicinity of a single catalyst particle. This is the same catalytic process seen in another way, where you can see the fluid-solid film, which is useful for modeling mass transfer effects later, because we can just assume that diffusion takes place in the film only. The properties are uniform throughout the bulk fluid. Here, the blue region is the fluid phase, the gray region is the solid phase, and the orange rectangle represents the surface of the catalyst or an active site. Let's look at the 7 steps. Step 1, reactant A in the bulk fluid has to migrate to the surface of the catalyst pellet through the film. Step 2, A then diffuses through the pores in the catalyst. Step 3, A can then adsorb onto the catalyst surface, and step 4, A reacts to form B. Step 5, B can then desorb from the surface of the catalyst. Step 6, B has to diffuse through the pores, and 7, diffuse through the film to reach the bulk fluid. Can you sketch the steps for the catalytic process in a three-phase reactor? Think about it, but don't do it now, as this will be an exercise in our in-person session. So now we know all the steps that can take place. We want to know what the overall rate of catalytic reaction will be, because that's what we need to design the reactor. The overall rate of catalytic reaction is equal to the rate of the slowest step. The slowest step is called the rate-limiting step or rate-determining step because this is the step that limits or determines the overall rate of reaction. We have two general cases. The first one is the rate of reaction is insignificant compared to the rate of mass transfer. For example, internal and external diffusion. Here, the reaction is very slow, so the reactants have time to diffuse through the pores and build up at the active sites. Product can only be formed at the rate that the surface reaction can proceed. This is called chemically controlled because it is the chemical reaction rate that controls the overall rate. In this lecture, we will focus on this case so that we can learn how to predict the rate of surface reaction. In subsequent lectures, we will add the internal and external diffusion steps to see how to determine the overall rate. In the second case, the rate of reaction is much faster than the rates of diffusion. The reactants arrive at the active sites relatively slowly, and therefore they can be consumed by the reaction as soon as they arrive. The case is called mass transfer controlled because it is the rate of mass transfer that is limiting or controlling the overall rate of reaction. A good analogy is being at Yo Sushi. The food can be thought of as the reactant. The conveyor belt is the mass transfer, and you or the diner eating the food is the reaction. If the conveyor belt is too fast and you cannot eat the food quickly enough, then the food will accumulate on the conveyor. The rate at which the food disappears is the same as the rate you can eat it. But if you're hungry and you can eat faster than the food arrives, then each time a dish comes along, it's gobbled up right away. You have to wait for the next dish to come along, so you can only eat as fast as the food is delivered, and the overall rate of food consumption is controlled by the conveyor speed. The catalytic reaction can be broken down into three individual steps: adsorption of reactant, surface reaction, and desorption of products. Note that steps 3 and 5 are chemical adsorption and desorption, so they involve making and breaking of chemical bonds. Again, in this lecture, we are considering that the catalytic reaction, comprising steps 3, 4, and 5, is the limiting step. So how do we estimate the rate of reaction? To estimate the rate of reaction, we will use two different models, the Langmuir Hinshelwood mechanism and the Eley Rideal mechanism. In the Langmuir Hinshelwood mechanism, two reactants are adsorbed onto the surface and then react on the surface. So again, two reactants need to be adsorbed. In the Eley Rideal mechanism, one reactant is adsorbed and the other remains in the fluid. They react when the fluid reactant collides with an adsorbed reactant. We will talk about these mechanisms in detail, but for now, reaction rates are described more generally as follows. We can think of the reaction being controlled by three factors: the kinetic term, the driving force term, and the adsorption term. To illustrate this is an example rate expression. We will derive this in detail, but for now, just look at the form. Here is the kinetic term, which is related to the intrinsic reaction rate. K subscript Fr is the rate constant of the forward reaction. A driving force term, which is related to the concentrations of the reactants and products and describes how close the system is to equilibrium. Capital K is the overall equilibrium constant. And finally, an absorption term, which accounts for all of the species being adsorbed on the catalyst surface and competing for active sites. That is, the reactants cannot always find active sites on which to adsorb. Note that this term is sometimes called the inhibition term because the other species adsorbed on the active sites prevent or inhibit the reactants getting to the sites. As this term is in the denominator, the larger it gets, the slower the rate is. Here, KCA, KCB, and KCP are the adsorption equilibrium constants. Ca, Cb, and Cp are the bulk concentrations of the reactants and products. An empirical way of modeling the reaction rate is to use a power law. This is easy to fit to experimental data using log-log plots. You have done something similar before. As you can remember, you can transform this power law to a linear equation by taking the logarithms of both sides. And then you plot points based on your data and fit a trend line and then get the slope and y-intercept and compute the reaction order and rate constant from them. But it is often not very accurate over a wide range of conditions. For example, the log-log plots may not be straight lines. You typically fit a trend line, so this model is approximate. More importantly, empirical models cannot explain the mechanism of how the reaction happens. So, more mechanistic or physics-based models have been developed, and two very popular and useful ones are the Langmuir, Hinshelwood, and Eley Rideal kinetics. They are suitable for wide ranges of concentrations and also for consecutive reactions with intermediates. They provide some understanding of the mechanism of how the reaction happens. Langmuir and Hinshelwood both received Nobel Prizes for their work in surface chemistry and chemical reaction mechanisms. You can see how long ago that was, and we are still using their mechanisms. First, we need to understand adsorption and desorption. In this diagram, there are only adsorption and desorption. Surface reaction is not included yet. So, adsorption and desorption can be seen as reactions between species in a fluid phase and active sites on the surface of a catalyst. In fact, it is called chemisorption if chemical bonds are formed between the molecules and the active sites, whereas if there are only physical forces causing the species to adsorb, then it's called physisorption. Here, it is chemisorption. Adsorption takes place right next to the surface of the catalyst. For non-porous catalysts, this is the external surface of the pellet. For porous catalysts, this is inside the pores and onto the internal surfaces of the pores. So, if species A adsorbs onto the catalyst surface, we say that A reacts with a vacant site or vacant active site S on the catalyst surface and forms the product AS. A is now bound to the site S, and S cannot be used to adsorb anything else until A is released. A is in the fluid phase, meaning it could be in liquid or gaseous phase. S and AS are in solid phase, which is the catalyst surface. The rate of adsorption is denoted by R subscript A, which is equal to the adsorption rate constant, Ka, times the bulk concentration of A, Ca, times the concentration of vacant sites, Cs. The reverse reaction is desorption, and its rate is denoted by R subscript D. And this is equal to the desorption rate constant, Kd, times CAS, which is the concentration of active sites occupied by A. Here we expressed everything in terms of concentration. But if we have a gas phase, it is more convenient to express the composition of the gas phase using partial pressure. We can convert concentration to partial pressure using the ideal gas law. A common mistake that students make is converting all of the concentrations to partial pressure. Note that you cannot convert liquid and solid or surface concentrations to partial pressure. Only gas phase has partial pressure. The common convention is to use partial pressures to express composition in the gas phase and concentrations C for liquid and solid phases. The Langmuir isotherm describes the equilibrium between adsorbed and free molecules. The Langmuir isotherm determines the surface coverage or fraction of the surface of the catalyst that is covered by adsorbed species at a given temperature and pressure. To get the equilibrium, we need to equate the forward and backward reactions. So the rate of adsorption, Ra, is equal to the rate of desorption, Rd. We don't want to keep track of two surface concentrations, Cs and CAS, because they are very difficult to measure. We can replace one of them with CT, the total number of sites, which is a constant. We can do that by writing a site balance. The total number of sites, CT, is the number of free sites, CS, plus the number of occupied sites, CAS. Now we can write CS in the adsorption rate as CT minus CAS and get the following equation by equating the forward and reversed rates. To recap, we have represented adsorption and desorption in terms of reaction. So we have A, which is the species in the fluid phase, reacting with a vacant active site S, forming the adsorbed species AS. Okay? So the forward reaction is adsorption with a rate constant of Ka. And the reversed reaction is desorption with the rate constant Kd. So we can write the rate of adsorption by Ra. So this is just equal to the rate constant of adsorption. So that's Ka multiplied by the concentration of A and the concentration of the free active sites. Similarly, the rate of desorption is equal to the desorption rate constant multiplied by the concentration of the site occupied by the adsorbed species, CAS. So these are in terms of concentration. Okay, so however, if A is in the gas phase, it is more convenient to represent its composition using partial pressure. And we can convert concentration to partial pressure using the ideal gas law. Okay, so doing that, we'll have Ra is equal to Ka Pa over RT times Cs. So that means that Ra is equal to Ka prime Pa Cs. Okay, and here Ka prime is equal to Ka over RT. Okay, so the prime denotes that the concentration of A, or the concentration of the bulk phase or composition of the bulk phase, is now expressed in partial pressure. So for the rate of desorption, there are no composition here for the bulk phase or for the gas phase, but it's good to be consistent and represent Kd as Kd prime so that we know that the composition of the gas phase or the bulk phase is expressed in terms of partial pressure. So let's do that. So Rd, that's equal to Kd prime. So prime to denote that the composition are expressed in terms of partial pressure. So Kd prime Cas. Okay, so therefore Kd prime is just equal to Kd. So now let's derive the Langmuir isotherm. As I've said, this can be used to determine the surface coverage or the fraction of the catalyst surface that is covered by adsorbed species. The Langmuir condition states that the adsorption is in equilibrium with desorption. So that means that the rate of adsorption, Ra, is equal to the rate of desorption, Rd. So we can use the expressions that we have derived earlier for RA and RD. So RA is equal to Ka prime PA times CS, and RD is equal to KD prime CAS. So here I have two surface concentrations, CS and CAS, but they are very difficult to measure. So I would like to replace one of them with CT. CT is the total number of sites, and it is a constant if catalyst deactivation can be neglected. So performing a site balance, the total number of sites is CT equal to the number of free sites plus the number of sites occupied by A. So that's CAS. And then we can solve this for CS and substitute this to the CS in this expression. So now I will rearrange that so that all CS are on one side. So I'll have Ka prime, Kpa Ct, and I will move the CS to the right hand side. So I have Kd prime, and then this is minus here, so this will become positive when I move it to the other side. So I'll have plus Ka prime Pa, all of this multiplied by CAS. What I would like to determine is the surface coverage, which is again the fraction of the catalyst surface covered by the adsorbed species. And in our notation, that is CAS over CT. And I will denote this as theta A. So this is our surface coverage. And I can solve this from this expression. This is just equal to Ka prime Pa over Kd prime plus Ka prime Pa. So here I have rate constants, Ka prime and Kd prime, but they are very difficult to measure. So I would like to replace them with the equilibrium constant because equilibrium constants are easy to measure. So you just leave your system and wait for it to reach equilibrium and measure the compositions and calculate your equilibrium constants. Whereas rate constants, so the small case, are very difficult to determine, especially for fast processes. The equilibrium constants can be related to the rate constants. Okay, so for adsorption, the equilibrium constant can be denoted as K, capital K, subscript A, and this is equal to, by definition, the ratio of the forward and the backward rate constants. So I can write this as Ka prime, Kd prime. So now I would like to transform this so that I have equilibrium constants in the expression rather than rate constants. So I can multiply the top and the bottom of the equation by 1 over Kd prime. Okay, 1 over Kd prime. Okay, actually our notation has P here. Okay, so Kpa, equilibrium constant Kpa, to indicate that the bulk phase concentration is in terms of partial pressure. Okay, so please do not forget that. So if it's in terms of concentration, there will be a C here. Okay, so going back to this, I can now evaluate this. So my surface coverage theta A. This is equal to Ka prime over Kd prime times Pa divided by Kd prime over Kd prime plus Ka prime Kd prime Pa. So now I can just simplify this because Ka prime over Kd prime, by definition, that is the adsorption equilibrium constant. So I can write this as theta A, so that's my surface coverage, CAS over CT. This is equal to capital Ka, or Kpa, Pa, okay, all over 1 plus K, Pa, Pa. And this is my Langmuir isotherm. We can use this to determine the fraction of the catalyst surface covered by the adsorbed species A at a given temperature and pressure. This is the Langmuir isotherm that we just derived. As before, you can also use concentrations with equivalent adsorption equilibrium constant, Kca equal to Ka over Kd. Note that when it is in terms of the concentration, we use subscript C in the adsorption equilibrium constant, and the rate constants do not have primes. When it is expressed in terms of partial pressure, we use subscript P in the adsorption equilibrium constant, and the rate constants have primes. As I said before, the Langmuir isotherm describes only adsorption and desorption and not surface reaction. Do not confuse it with the Langmuir-Hinshelwood mechanism, which comprises adsorption, surface reaction between two adsorbed reactants on catalyst surface, and desorption. We will talk about the Langmuir-Hinshelwood mechanism in detail shortly. However, if you have a unimolecular reaction, such as a decomposition reaction, where A goes to B, you can use the Langmuir isotherm to get the concentrations to use in the rate expression. As we talked about before, if the rate of reaction is much slower than the rate of adsorption, then the reactant A will accumulate on the catalyst surface and reach equilibrium. Each time AS is consumed by the reaction, another A quickly arrives at the surface. So if we have a first order reaction, A goes to B, then the overall rate of reaction is simply given by Ra equal to K times theta A, where theta A is the equilibrium coverage of A as given by the Langmuir isotherm expression. Again, this only applies if the reaction rate is much slower than the adsorption and desorption rates. So the product B needs to desorb quickly to free up the sites so that the isotherm is correct. Otherwise, we need to include the adsorbed product B in our site balance. We will look at this situation later. So now, let's expand the Langmuir isotherm to include surface reaction between two adsorbed reactants. This will become the Langmuir-Hinshelwood mechanism. The Langmuir-Hinshelwood mechanism has three key assumptions. It has to be a reaction between two adsorbed molecules on the catalyst surface. All steps, the adsorption, surface reaction, and desorption steps must be reversible. The surface reaction step is the rate limiting step, and all others, that is, the adsorption and desorption steps, are in equilibrium, such as in the Langmuir isotherm. Let's start with a simple bimolecular reaction. A plus B goes to AB reversibly. The first step is for the reactants A and B to get adsorbed onto the catalyst surface. These reactions describe the reversible adsorption and desorption of A and B. Note the notations for the rate constants. As before, we are using small a and d to indicate adsorption and desorption. But now, there are more than one adsorbed species, so we need to indicate whether the rate constant is for component A, B, or the product AB. Now we write the net rate of adsorption, which is equal to the rate of forward minus the rate of backward reactions. So the net rate of adsorption of A can be written as R subscript small a for adsorption, comma, capital A for component A, equal to the rate of the forward step, which is adsorption. So that is the rate constant for the adsorption of A times the bulk concentration of A times the concentration of the vacant sites, minus the rate of the backward step, which is desorption. So we have the rate constant for the desorption of A times the concentration of the sites occupied by A. We can write exactly the same thing for B. So the net rate of adsorption of component B is equal to the rate of adsorption of component B, given by this term, minus the rate of desorption of B, given by this term. So now the two adsorbed species, AS and BS, must come together and react, forming ABS, which is the product component adsorbed onto the surface of the catalyst. Note that this reaction releases one site S. The surface reaction is reversible, which is one of the assumptions of the Langmuir-Hinshelwood mechanism. And the backward reaction is ABS reacting with a vacant site S, forming AS and BS. The net rate of reaction is the forward rate minus the backward rate. If we denote the rate constant for the forward reaction with K subscript FR and the rate constant for the backward reaction with K subscript BR, then the net rate of surface reaction, R subscript R, can be written as the rate of the forward reaction, which is the rate constant, KFR, times the surface concentration of A, CAS, and the surface concentration of B, CBS, minus the rate of the backward reaction, so that's the rate constant, KBR, times the surface concentration of product AB, that's CABS, and the concentration of the vacant site, CS. In a bimolecular reaction, the rate of reaction depends on the product of the concentrations of both species involved, which makes bimolecular reactions second-order reactions. Remember, when AS reacts with BS to give ABS, it releases one site, so don't forget that CS appears in the reverse rate. The final step is desorption, where the adsorbed ABS dissociates and the product AB is released along with an active site. Note that the forward step is desorption with a rate constant KdAB, and the reverse step is adsorption with a rate constant KaAB. We write the net rate of desorption as the rate of the forward step, that's KdAB times the surface concentration of AB, so CABS, minus the rate of the backward step, so that's KaAB times the bulk concentration of AB, so CAB, times the concentration of the vacant sites. Getting the expressions for the individual steps of adsorption of reactants, surface reaction, and desorption of product is the first step in deriving the overall reaction rate. This is quite important, so let us practice with an example. So now we have an activity where I would like you to think about the mechanism for the oxidation of carbon monoxide over a rhodium-3 catalyst using the Langmuir Hinshelwood mechanism. So write down the rates of adsorption of O2, adsorption of CO, surface reaction of O with CO to produce CO2, and the desorption of CO2. Pause the video now and write down your expressions. I chose to give you this example to illustrate some points that you can have several possible mechanisms. For example, when you have a diatomic molecule like O2 here. Several things can happen, and here are two possible mechanisms for adsorption of O2. In the first mechanism, O2 binds to two active sites and then dissociates rapidly. It is a reversible reaction, so if there are two OS close to each other, then the O atoms can recombine to form O2. In another mechanism, mechanism 2, the O2 binds slowly to a single site, and then the O2 dissociates, and the free O radical quickly finds another site S to adsorb onto. The latter step, where the O2 radical attaches to another S, is very fast compared to the dissociation of O2. So we can ignore this step. For this mechanism, we can write O2 plus 2S reversibly goes to 2OS. Okay, so the rate constant of the forward step we can write as Ka O2, and the backward step is Kd O2. Okay, so we can write the net rate of adsorption of O2 is equal to K KaO2 times the concentration of O2 times the concentration of the vacant sites squared. Okay, so minus the reverse step, which is KD O2. Okay, so times the concentration of OS. Okay, so again, we have the 2 stoichiometric coefficient there. So we can write 2. Okay, so for the mechanism 2, so we can write O2 plus 1 free site. Okay, reversibly going to just 1 OS. We're going to ignore these parts. Okay, OS. And the rate of adsorption of O2 using this mechanism is equal to, okay, so Ka. So again, the rate constant for this is KaO2, and this one is KdO2. Okay, so KaO2 times the concentration of O2 times the concentration of the vacant sites. This is minus the reverse rate, which is KdO2 times the concentration of OS. Both of these mechanisms have been proposed for this reaction. This second one was validated by experiments. So this is first order. So the rate expressions are simpler. So if a question asks you to postulate a mechanism, then either of the two would be acceptable. The point is that in practice, you should postulate as many mechanisms as make sense and then use experiments to determine which one is actually occurring. Now let's write the expressions for the other steps, which are straightforward. Okay, so adsorption of CO we have CO plus S going to COS. Okay, so we write the adsorption and desorption rate constants. So this is KA CO and this is KD CO. And the rate expression is, okay, net rate of adsorption of CO. It's equal to RA CO. This is equal to the forward step. So that's KA CO times the concentration of CO times the concentration of the vacant site minus the reverse rate. So that's KD CO times the concentration of COS. Okay, so surface reaction. We have OS, okay, from this step, reacting with COS from this step. Okay, this is also a reversible reaction, and CO2S plus S are formed. So the rate constant for the forward reaction is KFR, and the rate constant for the backward reaction is KBR. We can therefore write the rate or the net rate of the surface reaction, so RR, this is equal to the rate of the forward reaction, so that's KFR times COS, CCOS, minus the rate of the reversed step, so that's KBR, concentration of CO2 S times, okay, so don't forget this guy, concentration of the vacant site. And then finally, we have the desorption of CO2. Okay, so in this step, the adsorbed CO2 or CO2S from the surface reaction step so it dissociates into our product, CO2, and it releases one free active site. Okay, so let's write the rate constants. So the forward step is desorption. So we write, okay, so rate constant of the desorption of CO2. Okay, and the backward step is adsorption of CO2. So we write K adsorption of CO2. Okay, and we can write the net rate of desorption of CO2 as, okay, so R desorption of CO2, this is equal to the forward step, the rate of the forward step, which is KD CO2 times the concentration of CO2S minus the rate of the reverse step, which is Ka CO2 times the concentration of our product, CO2, and concentration of the vacant site. Here are the solutions that we just derived. Now, to carry on with the derivation of the overall rate of reaction for the Langmuir-Hinshelwood mechanism, we want to define a general equilibrium constant for the overall process. We want the equilibrium constant, so big K, because they are easier to measure than the rate constants, the small k's. So just wait for equilibrium and then measure the composition. The rate constants, on the other hand, are very difficult to measure, especially for fast processes. By definition, an equilibrium constant is the ratio between the forward and the backward rate constants. Using this definition, we can write the equilibrium constants for each of the steps as follows. So for the adsorption of A, the equilibrium constant is capital K A equal to the rate constant for the adsorption of A divided by the rate constant for the desorption of A. And we can define the equilibrium adsorption constant for B in a similar manner. The equilibrium constant for the surface reaction is capital KR, and this is equal to the ratio between the rate constant for the forward reaction and the rate constant for the backward reaction. And then finally, we have the equilibrium constant for the desorption of D. So this is capital K D, and this is equal to the rate constant for the desorption of our product, AB, divided by the rate constant for the adsorption of AB. Note that the desorption constant is the inverse of the adsorption constant. So now we can write the net rates of each step in terms of the equilibrium constants. But before that, let's have a recap. So we have the overall reaction, A plus B goes to AB, which we can represent in 4 steps. So the first step is the adsorption of A. A plus S goes to AS. Equilibrium constant is KAA and KDA. Second step is the adsorption of B. That is B plus S goes to BS. Rate constants K adsorption of B and K desorption of B. Third step is the surface reaction between AS and BS. So we write AS plus BS goes to ABS plus S. Rate constants KFR and KBR. And then fourth step is the desorption of ABS. So we have ABS goes to our product AB plus S. Rate constants, so KD, AB, and KA, AB. So now let us write the net rates of each step. So for the first one, so net rate of adsorption of A, that is equal to KAA, CA, CS minus KDA, CAS. Okay, so for the second step, net rate of adsorption of B is equal to K, AB, CB, CS. Okay, backward step, so that's KD, B, CBS. Okay, so net rate of surface reaction for step 3. So that is RR. Okay, so forward reaction, KFR, concentration of AS, concentration of BS, minus KBR, concentration of ABS, concentration of S. And then finally, for the desorption step, net rate of desorption RD, this is equal to the forward reaction. So that's KD AB times CABS minus KA AB times concentration of AB times CS. Okay, so now that we have the net rates, let's express them in terms of the equilibrium constants. So I can do that by factoring out the forward rate constants. So let's do it for A. So I can factor out KAA. So I will have CA, CS minus KD, A. Okay, so KAA and CAS. Okay, but this is just the inverse of our adsorption equilibrium constants. So this is equal to KA, A, CS, CA, CS minus CAS divided by our equilibrium constant A. Okay, so here note that equilibrium constant A is equal to KAA all over KDA. Okay, so let's do the same thing for B. So I can write this as KAB. Okay, so CB, CS minus KDB, CBS divided by, okay, so KAB. Okay, so again, this is the inverse of our equilibrium constant. So I can write this as KAB, CS minus CBS divided by our adsorption equilibrium constant for B. Okay, so here we have KB equal to KAB divided by KDB. Okay, so let's do it for the surface reaction. So I can factor out KFR. And I will have CAS, CBS minus CABS, CS over K. Okay, so I have KBR here. And I'll have KFR here. Okay, but I know that the equilibrium constant for the surface reaction KR, this is equal to KFR over KBR. So I can write this. So this is just equal to KFR times CAS, CBS minus CABS, CS all over the equilibrium constant for the surface reaction, KR. And then finally, for the desorption step, so I can write this as KD, AB. I'll have CABS here minus KA, AB, CAB, CS divided by KD, AB. Okay? And for desorption, the equilibrium constant KD is equal to KD, AB divided by KA, AB. So I can write RD. Okay, so this is equal to KD, AB times CABS minus CAB, CS. Okay, and this is just our KD. So here are the net rates for the 4 steps in terms of the equilibrium constants. We can see that the rates all involve surface concentrations. So we have CAS, CBS, CABS, and CS, which are very difficult to measure. And we would rather relate them all to fluid concentrations or partial pressures. To do that, let's use the assumptions from the Langmuir Hinshelwood mechanism, which states that the rate of surface reaction is low compared to the rates of adsorption and desorption. Okay, so Langmuir Hinshelwood mechanism. Okay, so states that the surface reaction is the rate limiting step. Okay, so RR, this is our rate limiting step. While the rates of adsorption and desorption, RA, A, RAB, and RD, these are all 0 because they are all in equilibrium. Okay, so that means that we can take this. So RAA, which we have written to be equal to this. Okay, so we have K AA, CA, CS minus CAS all over KA. Okay, so this is our AA, and this is equal to 0. Okay, so therefore, from this, we can say that CAS is equal to KA, CA, so this is the bulk concentration, times CS. Okay, so we can do the same thing for B. So our AB is equal to this. So this is actually CB. Okay, so KAB have CB, CS minus CBS all over KB. This is equal to 0. So we can get our CBS, which is equal to KB, CB times CS. Okay. And then finally, our RD, rate of desorption, which we wrote this way. So that's KD, AB, CABS, that's CAB, CS, KD. This is equal to 0, so we can therefore solve for CABS, which is equal to CAB, CS all over KD. Here are the surface concentrations in terms of the bulk concentrations. So we have the expression for CAS, CBS, and CABS. I would like to replace CS with CT, the total number of sites, because CS is very difficult to measure, while CT is constant if we assume that catalyst deactivation can be neglected. Let's perform a site balance to get an expression relating CS and CT. The total number of sites, CT, is equal to the number of free sites, CS, plus the sites occupied by A, CAS, plus the sites occupied by B, CBS, plus the sites occupied by our products, AB. The surface concentrations, CAS, CBS, and CABS, are given by the expressions that we derived earlier, so we can substitute them into our equation. Okay, so I have just substituted CAS from here, CBS to here, and CABS to here. And then I can factor out CS. So therefore, if I move this term to the denominator of CT, CS is equal to CT divided by this whole term here. Now let's derive the overall rate of reaction, negative RA. This is also sometimes called the global rate or the observed rate. According to the Langmuir Hinshelwood mechanism, the overall rate is equal to the rate of the limiting step, which is the surface reaction. Earlier, we derived an expression for the rate of the surface reaction in terms of the surface concentrations and the equilibrium constants for the surface reaction. So I will write that here. So this is equal to KFR times CAS CBS minus CABS times CS all over the equilibrium constant for the reaction. I would like to eliminate the surface concentrations and replace them with the bulk concentrations. So earlier, we derived the expressions for the surface concentrations in terms of the bulk concentrations. So I can use them here. So I can write this as negative RA. This is equal to KFR times CAS is just KA CACS. CBS is KB CB CS. CABS is CAB CS all over KD. Okay, and we have some more terms here, which I will bring down. Okay, so CS over KR. Okay, so I have CS square in each term. So I can bring that out of the brackets. So this will become KFR. And then I'll bring out CS square. This will become KA, KB, CA, CB, minus CAB divided by KD all over KR. I can replace CS with CT. I prefer CT because if we don't consider catalyst deactivation, then it is just a constant. Whereas CS is very difficult to measure. So we can use the expression that we derived earlier for CS as a function of CT. So I'll substitute that here. So this is equal to KFR. So CS square will become CT square. Okay, and then I have this denominator here. So I'll have 1 plus KA CA plus KB CB plus CAB all over KD. And I have to square it. Okay, because CS is squared here. And then I will just bring down the rest of my terms here. This is the expression that we just derived for the overall rates. We are nearly done, but it would be nicer to relate everything to the overall equilibrium constant K, which is in terms of the fluid concentrations instead of the surface reaction equilibrium constant Kr. As you will remember, we can also define the equilibrium constants as product of the concentrations of the products divided by the product of the concentrations of the reactants. Using this, we can define all of the equilibrium constants as follows. For example, the adsorption equilibrium constant, Ka, is the concentration of the product in that step, which is CAS, divided by the concentrations of the reactants in that step, which are Ca and Cs. Same thing for Kr. We have the concentrations of the products in that step in the numerator and the concentrations of the reactants in the denominator. All of the equilibrium constants here are measurable, except for Kr. Note that we can use the Langmuir isotherm for the adsorption or desorption equilibrium constants. For Kr, however, since the surface reaction is intermediate between adsorption of reactants and desorption of products, the surface concentration in the expression are very difficult to measure. So, we will replace Kr with the overall equilibrium constant K, which is purely a function of the bulk concentrations. It is very easy to measure. In fact, for a given temperature, it can be calculated from the Gibbs free energy. We need to do some algebraic juggling to relate them all and put our rate expression in terms of the overall equilibrium constant and the adsorption constants. Here is our overall reaction and 4 individual steps. We can write the overall equilibrium constant for the overall reaction as K. And this is equal to the concentration of the product, CAB, divided by the product of the concentrations of the reactants. So we have Ca times Cb. Similarly, we can write the equilibrium constants of the individual steps. So we have Ka for adsorption, and that is equal to the concentration of the product in that step, which is CAS, divided by the product of the concentrations of the reactants in that step. So we have CAS or Ca times Cs. We can do the same thing for the adsorption of B. So we have Kb, and this is equal to Cbs divided by Cb times Cs. For Kr, we have CABs times Cs divided by CAS times CBS. And for the desorption, KD, we have CAB times CS divided by CABS. So now, let's multiply the equilibrium constants for the individual steps. So we'll have Ka times Kb times Kr times Kd. Ka is CAS, Ca over Cs. Kb is CBS over Cb, Cs. KR is CABS, CS, all over CAS, CBS. And KD is CAB times CS divided by CABS. Okay, so you will see that we can cancel out the surface concentrations. CAS, CBS, CABS, and the terms for CS. So we have 2 in the numerator and 2 in the denominator. So we are left with CAB in the numerator and CA times CB in the denominator, which are all bulk concentrations. And in fact, this is the definition of our overall equilibrium constant, K. So therefore, we can write KD times KR is equal to K all over KA times KB. Okay, I need it in this form because if you can remember, our overall rate of reaction here has this term, okay, KD times KR. So therefore, I can write this term CAB over KD times KR okay, so this is just equal to KA, KB, CAB all over K. So I can substitute this into my overall rate expression and get rid of the surface reaction equilibrium constant and express that in terms of the overall equilibrium constant, K. This is the relationship that we just have derived. So, let's replace the surface reaction equilibrium constant, Kr, with the overall equilibrium constant, K, by substituting this expression into this. So we will have negative Ra equal to KFR Ct squared multiplied by Ka Kb Ca Cb minus, so I will replace this term with Ka Kb Cab all over K divided by 1 plus Ka Ca plus Kb Cb plus Cab Kd squared. So I would like this to be in the form showing the terms for kinetics, driving force, and adsorption. Okay, so what I can do is I can take out Ka times Kb. I can take them out of the bracket. So this will become negative Ra equal to KFR Ct squared Ka Kb Ca Cb minus, okay, so I'll take out Ka Kb. So this will become Cab over K all over the denominator. If you can remember, this is the final form of our rate expression for the Langmuir-Hinshelwood mechanism. So here we have our kinetic term. This is the driving force term, and this is the adsorption term. Again, this is the final form of the rate expression for Langmuir-Hinshelwood mechanism. So now all of the equilibrium constants and concentrations are measurable quantities. We spent some effort deriving it, but it is worth it because we need the rate expression to design our reactor. This is something that I would like you to do in your own time. Can you derive the Langmuir-Hinshelwood rate expression for a gaseous reaction, assuming ideal gas? Please use the correct notations. K prime for the overall equilibrium constant in terms of partial pressures, and KPIs for the adsorption equilibrium constants. Put it in a form showing the terms for the driving force, kinetics, and adsorption. Once you have done it, please take a photo of your answer and post it on our Padlet board. I will stop here now, and in the next lecture, I will cover the second part of this topic. I will teach you a faster way to derive the overall reaction rate expressions without having to go back to first principles. Then we will continue looking at the Langmuir-Hinshelwood expression, and we will move on to derive the Eley-Rideal rate expression. And then we will solve some example problems.